Hello. In this module, we'll discuss Chapter 2, where mass, energy, and entropy balance equations are developed, and we analyze closed steady systems. Okay, so we begin with mass and energy balance equation, and for that purpose, we'll start with an animation of a generic system. We go to Chapter 2, and the first animation is about a generic system. Let me just explain what I mean by that. At first look, it seems a very complicated system, but always remember, take a look at the boundary of the system to understand a system, and take a look at what is going on. You can see that there is mass entering here, there is mass coming out here. Also, there's shaft work transfer, there's electrical work transfer. Look at the boundary, what's crossing. And as you can see, there is some boundary work transfer here. So all this, and plus the heat interactions, heat is being transferred to the system, as we can see. So all these things can make a system very complicated. First of all, whenever there's a mass transfer, we call the system an open system. So it's an open system. Also notice that because of all these interactions, the system is changing with time, which is shown here by the change of color of the system. So you can think like all the properties at this given point versus that point could be different. So there is a spatial variation of properties, as well as there's a temporal variation. At a given location, if you concentrate at the color, you'll see from green it's becoming yellow to red. So that means the state at a given point is changing with time, and state at a point is different from state at another point. So this can be the most complicated system. Any system, any practical system such as a turbine, as a pump, a compressor that we are going to learn how to analyze is going to be much simpler than this. So if we can develop the governing equations, the fundamental laws of thermodynamics for this generic system, then we are ready to tackle any system, any practical system we are going to encounter. So let's begin by developing the conservation of mass, the mass balance equation for such a complex system. Obviously, when you talk about mass transfer, we don't need to think about all these different kind of work transfer and heat transfer. So before we develop the equation, let's just rehash some of the concepts we already covered. Recall that this formula is very well known. Mass flow rate is given by m dot is given by rho AV, which we developed in the last chapter. And the formula derivation is very simple. M dot equals rho AV should be a formula that you're very familiar with by now. And as you can see, to derive, you can derive it in one line, because if you think of this lump of fluid going through a given cross-section 1 in this case, as you can see, the amount of mass in this packet can be given by density times volume, which is area times the distance, the length of this lump of fluid. So therefore, the m dot is the mass that is crossing in delta t, and as you do the math, you can see, and the limit of delta t going to 0, it becomes density times an area goes out of the limit, and delta x over delta t gives us velocity. So the formula turns out to be rho AV. Simply speaking, in 1 second, how much fluid is going through, you can think like in 1 second, the amount of fluid that goes is given by rho AV. So this should be a formula, m dot equals rho AV, that you should be memorizing not only for thermodynamics, but all thermal science classes such as fluid mechanics, heat transfer. So this is a very, very important formula, where rho density is in kg per meter cube, area is in meter square, and velocity is in meter per second. As you can see, that gives us kg per second as our unit of mass flow rate. Okay, so let's go ahead and develop the equation now, the mass balance equation now. So the generic system we simplified here, very simple. There is no work crossing the boundary. There is no shaft work, electrical work, or heat transfer, only mass coming in and going out. I is the inlet state, E is the exit state. Of course, although we have shown here just one inlet and one exit, we can have multiple inlet or multiple exits. Okay, so let's go to time t. At time t, the mass of the system is given by mt. This is our mt is the time, so the system here is the red boundary. Whatever is within the red boundary is called our open system. So at the beginning of time, at the time t, we have the fluids inside this red system is empty, whatever that is. Excuse me. In time delta t, as you can understand, a little bit of fluid might have entered here, and the amount is given by m dot times delta t, m dot I times delta t, because the mass flow rate here is m dot I. That's the rate at which mass is going in, and in time delta t, this is the amount that will enter. How much will come out in that time? Just like m dot I, there is m dot E taking fluid out, so m dot E times delta t, mass flow rate times time is so many kg, right? Because this is kg per second and this is delta t. So many kg has come out and so many kg has gone in times delta t. So if you do an inventory of mass at time t plus delta t, is the original mass in the system plus what has come in minus what has gone out. A very simple algebraic summation of the total mass. So if we take this equation and do some algebra on it, then we can very quickly come up with what is known as the mass balance equation. So this is, to start with again, this is our mass at time t plus delta t. If we take mt on the left hand side and divide by delta t, we get the second equation. And then if I take a limit, delta t going to 0, then this term reduces to nothing but the classic definition of dm dt. And also, instead of one inlet and one exit, we can generalize that over many inlet and exit, resulting in what is known as the mass balance equation, dm dt. So let me write it down here. So what we have just derived is that dm dt equals summation of m dot I minus summation of m dot E. It's very important that we understand each term. So what is this term? This is the rate at which the system's mass is increasing, rate of change of mass of the system. This is the rate at which mass is entering the system through all the inlets, and this term is the rate at which mass is leaving the system through all the exits, summed over all the exits. So this is a very simple equation, but a simple application of could be, suppose we have a system, a mixing system. Suppose mass comes in through state 1, state 2, and goes out through state 3. And also let's say is given to us that m dot 1 equals 1 kg per second, m dot 2 is 2 kg per second, and let's say m dot 3 is 4 kg per second. And we are asked to find dm dt, the rate at which, so our system here is this. Even though it looks like a very boring system, think about it, it could be a combustion chamber where, let's say, methane is coming here and air is coming here, and they're burning and they're going out. The combustion products are going out at state 3. As far as mass is concerned, we don't care whether there's a chemical reaction or not. Okay, so what is our dm dt? The simple answer is, if I apply our mass equation, we get summation over m dot I. There are two inlets, m dot 1 and m dot 2 minus m dot 3. So the answer is very simple here, minus 1 kg per second. So what does the negative minus 1 mean? The negative 1 here means dm dt is negative 1 means the system's mass is going down every second by 1 kg. That's what it means. The system is losing mass, and that's clear from the sign. Okay, enough about mass conservation equation. So this is known as the mass balance equation. We'll come back to this equation many times and discuss several simplification of these equations. But first, let's derive the energy equation and entropy equation in the same format. Okay, to derive the entropy equation, we go back, to derive the energy equation, let's go back to the animation where we discussed transport. Let's just revise the transport equation quickly. If you recall, the mass that flows through a system, through any state, the mass flow rate, if you know the mass flow rate, you can also figure out, if you know the properties at a given flow state, the rate of transport of different properties. If you recall, in the last chapter, we derived the transport equation B dot equals m dot times B, where m dot is the mass flow rate and B is a specific property. So B could be, for instance, you can think of the kinetic energy transport. For instance, the flow can be carrying kinetic energy. The flow could be carrying potential energy, or E. So if you go to the energy transport, try to understand how energy is transported by mass instead of any generic property. We know that when mass crosses this cross section, it carries stored energy inside the system. So the lump has, in addition to mass, it is carrying this amount of stored energy. So therefore, E dot, the rate of transport, as you can see, is given by m dot times E. Whereas E, if you recall, is sum of kinetic potential and internal energy, and therefore you can show that E dot is U dot, K E dot, and P E dot. But when mass crosses a boundary, that's not all the energy that is crossing the boundary. There is also flow work that is being transferred. The flow work that is being transferred is given by, again, we have covered that in the last chapter, actually in chapter 0, is given by pressure times area times velocity, PAV. So this is the flow work formula. So the energy that really crosses a boundary is made up of two components, energy that is stored in the fluid and the flow work. As you sum them up, we get E dot plus WF dot to be J dot. So in other words, the total energy that is transported by a flow, that's called the flow energy. And the flow energy is given by J dot is given by m dot times J. So that's a simple formula. J dot, capital J dot equals m dot times J. So what is J? J is H plus Ke plus Pe. As you can see, we introduce a new term here because J is U plus E plus PV from this derivation. If you go substitute E dot and flow work, you get a formula J to be E plus PV, and E is U plus Ke plus Pe. And if you combine U and PV, that gives us H. H is U plus PV by definition. So in other words, just to summarize the net result, what we get is that whenever there is a flow, the energy carried by the flow is given by m dot times J. And what is J? It is summation of enthalpy, kinetic energy, and potential energy, all specific quantities. What is enthalpy? U plus PV. So that's something we have to memorize and remember so that you can apply that concept everywhere. Well, that prepares us for deriving the energy equation. So if we go, let's erase these markups. if we go to the generic system that we discussed, this time will include all kinds of energy transfer in addition to mass transfer. Again, we will concentrate on the red boundary and keep track of its energy. Over time delta t, what will happen? Some mass will bring in energy here. Some mass is going to take energy out there, and heat is going to bring in energy, and work is going to take energy out. Notice then heat and work are shown in the direction of positive transfer. If you recall the sign convention, Win-Hip, it means work in negative, heat in positive. So we are heat in is positive and work out is positive. Therefore, in this diagram, that's how we are showing heat transfer and work transfer. These are algebraic. In other words, in case heat is coming out, it will automatically become negative. If work is going in, it will become negative. Okay, so let's see how we derive the equation. At time t, as before, let's use ET as our symbol for energy stored in the system at time t within the red boundary. So what happens in time delta t? Some amount of energy will come in. How much? In delta t times the amount of mass that comes in is what? M dot I times delta t. That's the mass that comes in, and it carries specific energy. Specific flow energy is J, as you recall. So this is the amount that is carried in by the flow. Of course, it will be Ji because J has to be evaluated at the inlet. Similarly, this is the amount of energy that will come out in time delta t. Some work will go out. If W dot external is the rate at which work is going out in time delta t, this amount of energy will go out. And Q dot times delta t will be the energy that will be brought in by heat. So if we go to time t plus delta t, as you can anticipate, the new energy E at t plus delta t is the old energy, old stored energy, plus the amount that came in by the flow, the amount that went out by the flow, transported out by the flow, which is this amount, and then the energy that came by heat and the energy that left by work. So if we all that add up, the right hand side is equal the left hand side. In other words, this is the inventory of energy. We know energy cannot be created or destroyed, and that's the first law of thermodynamics. The only way in this system energy can change is because some energy may be transported in, some may be transported out. Heat can bring in energy, or work can take out energy. So therefore, just repeating the process that we did for mass equation, we will switch side, ET taking it to the left hand side, and we'll divide by delta t, and that sets us up for developing the rate equation or the balance equation. So notice that we get, as I take the limit, the EDT equals the transport terms, heat transfer and work transfer. So let me write that down in our notes, the energy equation that we just derived, and try to understand the meaning of each term. So dEdt, which is the rate at which the stored energy of a system can change, is given by the rate at which mass brings in, transports energy at all the inlets, minus the rate at which mass transports energy, the flow energy out of the system, plus, we are not using a summation sign, but it's understood that Q dot means sum of all the heat that goes into the system minus W dot external, the rate at which external work leaves the system. The unit is going to be kilowatt for each of these terms. So this is called the unsteady term, by the way. We'll learn more about this term later, which all it means is the rate at which the energy is changing. And these are called the transport terms. What are transport terms means? When mass flows, it carries with it a lot of properties. It transports flow energy in and out. And these are boundary heat transfer. These are called transfer terms. And this is work transfer terms. This is energy transfer by heat and work, external work. Notice that flow work is already absorbed in the definition of J. So the external work is made up of just shaft work, electrical work, and boundary work. And what is J? J is H plus KE plus PE, if you recall. What is H? U plus PV. And we have learned about all these properties already. And finally, what is capital E? Is the energy of a system given by KU plus KE plus PE. So this is so many kilojoule. These are units are kilojoule per kg. Of course, this will be kilowatt. So in short, this is our energy equation. We'll call this our energy balance equation, or in short, energy equation. It means the rate at which the energy of a system changes is given by the sum of the following causes. The causes are what? Energy can be added by transport of energy. Energy can be taken out by transport of energy. Energy can be added by heat. Energy can be taken out by work. Well, we can have so many examples of energy transfer by different ways. So for instance, a very simple diagram could be if somebody says, okay, explain, here's a system, tell me what is going on energetically. Here is state 1, a flow is coming, state 2, a flow is leaving, and then there's a pedal wheel that is turning, and let's say there's a candle that's hitting the system. So if the question is, take a look at this system and tell us what are the different terms of the energy equation here, you can say that, look, in this particular case, if I write the energy equation for this system, I'll write the EDT equals m dot 1 J1 minus m dot 2 J2 plus q dot minus w dot external, right? That will be the energy equation. What is m dot 1 J1? That's the J evaluated at this location and the mass flow rate. What is at state 2? Mass flow rate here may not be equal to mass flow rate at 1. So it's m dot 2 times J2. So these are the properties evaluated at the two flow states. What is q dot? The rate at which heat comes in. So suppose this power of this candle is a kilowatt, so q dot will be 1 kilowatt. And look at the pedal wheel. What is the pedal wheel doing? Do you think the work is coming into the system or going out of the system? Obviously, if you're turning the pedal wheel, you are doing the work, you are messing up the system, so energy is pouring in through the shaft. In that case, the shaft work, which is part of the external work, is going to be negative, because work in negative, heat in positive. That's the sign convention. Win hip. So if work comes in, it will be negative. So suppose we had all the numbers. Someone told us m dot 1 equals 1 kg per second, J1 equals 100, whatever unit, m dot 2 equals also, let's say, 1, J2 equals 50, q dot, the candle is putting, let's say, 2 kilowatt, and suppose the shaft work is 1 kilowatt. In that case, the equation will be 1 times 100 minus 1 times 50 plus q dot is 2 minus 1. Of course, I just made up all these numbers, but try to see and appreciate the way I substituted work as a negative number. So if the question is, find the rate of change of energy of the system, the answer will be the sum of these quantities. And the challenging task is to figure out what is J at a location. A lot of time you will see J will be same as H when KE and PE can be neglected, because as you know, J equals H plus KE plus PE. Try to memorize this formula. That will be quite handy for energy equations. Again, we'll come back to mass and energy equation big time after we cover entropy equation.